a collapsed, undefined, blurry mass, a gas giant whose layers blend into one another with a form that resembles abstract art more than scientific clarity. For a long time, Jupiter appeared in telescope images as nothing more than pastel-colored bands. There was no depth, no clear structure. Until the Juno space probe flew into those mists and began observing from within. When Juno entered Jupiter's orbit, it didn't just collect scientific data. Thanks to a camera called Juno Cam on board, it captured images that practically redefined how we see Jupiter. Then came Hubble's high-resolution color observations and James Webb's thermal scans in the infrared spectrum. Now, we no longer have just numbers about Jupiter. We have actual images, real, unprocessed, raw data. And yet, what formed in our minds through these data was unclear. Because the first images were so detailed, so vibrant, and so symmetrical that many thought they were illustrations or CGI renderings. But what we were seeing were direct captures through a machine's eye. The resulting images now gave the impression of a surface. The clouds didn't just stretch horizontally, they formed vertical structures. The storms didn't just move, they swelled and cast shadows. But the real question still stands. If this planet has no surface, what exactly are we looking at? If there's an impression of a surface, then beneath that impression, there must also be a system. And that system is hidden within the atmospheric bands that at first glance look like nothing more than colorful stripes. These bands stretch from Jupiter's equator to its poles, and they're not static. They're massive streams of gas in constant motion. Each one rotates in its own direction. They touch each other, but they don't mix. Driven by the planet's internal energy, these belts create their own set of rules. This atmospheric motion is very different from the winds we know on Earth, because here, there's no surface, no friction, no land barriers, no ocean boundaries. Instead, Jupiter's rapid rotation and internal heat guide massive jet streams, which are shaped by the planet's enormous Coriolis effect, meaning the directional deflection caused by Jupiter's rotation. Each band is like a colossal river of air, spinning at hundreds of miles per hour. And these rivers aren't limited to the horizontal. They also exist in the vertical dimension. Recent observations from the James Webb Space Telescope detected a previously unknown jet stream in Jupiter's upper atmosphere. Moving along the equator at speeds of over 300 miles per hour, this invisible current was discovered through a thermal trace in the infrared spectrum. And that trace isn't just a temperature difference. It's also a sign of vertical air movement from the top down. Within these structures lie cloud layers saturated with water vapor and ammonia. The color transitions are not just caused by the way light reflects, but by differences in chemical density. In some regions, rising hot air combines with ammonia. In others, cooling masses sink and form vortices. Every color indicates a temperature. Every swirl reflects a dynamic. So what drives this motion? If there's no surface, what is the atmosphere clinging to? In fact, the only things it clings to are speed and heat. Jupiter's atmosphere isn't shaped by a solid surface, but by internal pressure differences and rotational effects. The temperature imbalances that develop within this system eventually lead to massive turbulence. These turbulent flows form multi-layered systems that move not only horizontally, but vertically as well. In some regions, these systems evolve into stable storm structures. The most long-lasting example is the Great Red Spot, which has been observed for centuries. But it's not just a simple vortex. It has a layered flow system. The Great Red Spot is located in Jupiter's southern hemisphere. This storm system begins about 190 miles above the surface level and spins at speeds exceeding 250 miles per hour. There are differences in both temperature and speed between its layers. The upper gases are colder and more vividly colored. The lower layers are denser, hotter, and faster. Recent observations have shown that the storm is shrinking in width, but expanding vertically. This shift means the storm is growing taller, and some researchers now classify the spot as a storm skyscraper. But Jupiter's atmospheric fury isn't limited to massive storm systems. High-energy lightning discharges are also frequently observed in the planet's atmosphere. These lightning strikes occur both in the upper atmosphere and deep within the cloud layers. Similar to lightning on Earth, they emit light, but on a much greater scale and with far more energy. The Juno probe became one of the first instruments to directly observe these lightning events. Especially during its passes over the planet's night side, Juno's optical and radio sensors collected data simultaneously. The images captured sudden flashes, and at the exact same time, radio signals were detected. This match revealed that the lightning left not only a visual signature, but also an electromagnetic one. The formation of lightning is closely linked to the planet's chemical composition. Jupiter's atmosphere contains high concentrations of ammonia and water vapor. These elements are carried upward by rising warm air currents. At higher altitudes, they cool and condense. As they fall, they drag surrounding gases downward with them. During this process, particles form into dense ice clusters containing both water and ammonia. These are called mushballs. Mushballs play a critical role in lightning formation. As these falling particles descend, they accumulate electric charges at different altitudes, leading to sudden discharges of energy. Some lightning events aren't detected through optical sensors at all. They're picked up directly through radio frequencies. These strikes occur deep within the cloud layers, so they might not produce visible light. But radio waves can travel across much greater distances. These signals continue to be regularly recorded by Juno's instruments. So how can such powerful discharges happen without a solid surface? Is there a new energy source hidden in the lower layers of the atmosphere? The answer lies in Jupiter's unpredictable changes. Because the planet's atmosphere doesn't just express itself through massive storms, it also produces short-lived systems that appear suddenly and vanish just as quickly. Some jet streams form within days, gain speed, and then disappear without leaving a trace. Observations clearly show that Jupiter's atmosphere is not a static system. Even long-lasting storms like the Great Red Spot have been seen to change shape, shift direction, and lose energy over time. This evolution isn't just driven by external forces, it's also linked to the planet's internal heat transfer. Heat rising from within causes visible transformations in the upper layers. All of this data points to Jupiter's internal heat sources being more active than previously thought. That heat isn't just leftover energy from the planet's formation. It's also the result of ongoing dynamic processes near the core. These processes affect every layer of the atmosphere. They determine the direction of jet streams, the shape of storms, and the formation of lightning. So is Jupiter's extreme activity driven purely by internal heat? Or is the planet's structure fundamentally different from what we know about other gas giants? Jupiter's structure is different from that of known gas giants, because as we descend into the planet's depths, classical internal structure models begin to fall short. Density measurements and mass distribution analyses have revealed that Jupiter's inner layers deviate from expected symmetry. This deviation can't be explained by a simple core model alone. In fact, there's still no clear consensus about the nature of the planet's core. Some models suggest the presence of a compact, solid core larger than Earth. But gravitational data obtained by the Juno mission showed that this structure is more diffuse than expected. Based on this data, the hazy core hypothesis was proposed, suggesting that the core lacks a well-defined boundary. According to this model, the planet's center isn't just dense, it's also semi-fluid, transitional, and structurally ambiguous. Surrounding this core is a region where hydrogen exists in a very unusual phase. Jupiter's immense mass subjects the gas beneath its atmosphere to such extreme pressure that hydrogen, normally an insulator, becomes metallic. In this metallic form, hydrogen gains electrical conductivity and becomes the source of the planet's powerful magnetic field. However, the thickness, distribution, and behavior of this layer remain uncertain. So how did this irregular core come to be? Was Jupiter's internal structure disrupted by collisions during its early years? Or has the planet always been this way from the very beginning? If Jupiter's core was disrupted by violent collisions during its early years, the traces of that impact should be visible not only within the planet itself, but also on its surrounding moons. And the clearest evidence of that can be found on Io, Jupiter's innermost large moon. Io is the only celestial body in the solar system whose surface is entirely covered with active volcanoes. It has no stable crust. Constant eruptions, boiling lava lakes, and a shifting landscape reveal that this moon is constantly being reshaped. What makes Io so geologically active isn't its own structure, but the immense tidal forces exerted by Jupiter. Io undergoes a continuous stretching motion, not just from Jupiter's gravity, but also due to its orbital resonance with Europa and Ganymede. This motion generates friction within Io's interior, and that friction turns into heat. The heat melts rock and keeps the magma chambers perpetually active. As a result, the surface experiences frequent eruptions and flowing lava. Some of these eruptions blast materials hundreds of miles into space. A portion of that material escapes Io's gravity entirely, while the rest falls back down to form new lava plains. This ongoing transformation has been directly observed through time-lapse images captured by Juno in previous missions. In some cases, the surface of a single region looked completely different just a few months later. In this sense, Io isn't just a moon, it functions as an active part of Jupiter's energy transfer system. Every volcano on its surface is the result of a continuous energy exchange with the central planet. And the connection between Jupiter and Io isn't limited to gravity alone. There is a constantly operating, but invisible, electrical circuit between these two celestial bodies. Charged particles ejected from Io's surface into space interact with Jupiter's powerful magnetic field. As a result of this interaction, aurora structures form near the planet's poles, visible as glowing patterns in its upper atmosphere. So is this connection limited only to Io, or do Jupiter's other moons create similar effects as well? This connection isn't limited to Io. Dozens of moons orbiting Jupiter are in constant interaction with the planet's immense magnetic and gravitational fields. Each of these moons exerts a different influence on Jupiter's gravity, radiation belts, and magnetic field. The sum of these interactions requires us to consider Jupiter not just as a single celestial body, but as a far more complex system. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, move in orbital resonance with one another. These resonances affect more than just orbital stability. They also influence internal heating, surface tension, and even atmospheric processes. For example, it's believed that the subsurface ocean on Europa remains liquid due to tidal heating caused by these effects. Similarly, Ganymede is the only moon known to generate its own magnetic field, a feature it owes to its dynamic relationship with Jupiter. Jupiter's magnetic field is one of the strongest and most expansive known in the solar system. It's nearly 20,000 times stronger than Earth's and powerful enough to deflect charged particles from the Sun. What's more, this field doesn't just affect the planet's immediate surroundings, it directly influences the orbits of its moons. This structure means that Jupiter acts as a central hub, maintaining a self-contained system around itself. Within the solar system, only Jupiter generates a magnetic system of this scale independently. That's why many scientific models have begun to describe Jupiter not merely as a planet, but as a mini-system. And this system isn't limited to just physical interactions. It presents a structure where even the boundaries of biology may need to be redefined. Because the moons orbiting Jupiter are not ordinary satellites. Each one is a distinct world, shaped by Jupiter's magnetic and gravitational pressure, with its own unique features that surpass the typical limits of what we expect from a moon. Europa, with its subsurface liquid ocean, is one of the strongest candidates for meeting the criteria of habitability. The fractured structures on its surface suggest that liquid water beneath the ice is in motion. This movement could help renew the surface and potentially transport organic compounds upward. Moreover, Jupiter's powerful magnetic field may be heating Europa's interior, making it possible for this liquid layer to persist. This interaction points not only to geological activity, but also to the existence of an internal energy cycle with potential biological implications. Ganymede represents a different extreme. It is the only moon in the solar system known to generate its own magnetic field, evidence of a liquid metallic layer in its core. In addition, it's believed to contain multiple subsurface ocean layers, each possibly located at different depths. These layers may create a complex energy exchange between the surface and the core, a transition that could sustain a self-regulating environment. Callisto, on the other hand, though marked with some of the oldest cratered surfaces in the solar system, may have preserved its internal structure over long timescales due to low geological activity. This could increase the likelihood that it holds liquid water beneath the surface without being heavily exposed to cosmic radiation. And its low radiation level makes it a significant advantage for surface-based exploration. When considered together, could this central planetary body and its dynamic surrounding structures collectively form a kind of life system? Two new missions focused on Jupiter's complex system are preparing for launch. ESA's JUICE mission and NASA's Europa Clipper spacecraft are designed to explore regions within the Jupiter system that until now could only be observed from a distance. These missions will focus especially on three of the planet's four largest moons: Ganymede, Callisto, and Europa. ESA's JUICE mission was launched in 2023 and is scheduled to reach the Jupiter system in 2031. Throughout the mission, the icy surfaces, magnetic structures, and potential internal oceans of Ganymede, Callisto, and Europa will be studied. Ganymede in particular, with its unique magnetic field and the structural complexity beneath its icy crust, is one of the mission's primary targets. Once JUICE enters orbit, it will conduct long-term observations around Ganymede. NASA's Europa Clipper mission, meanwhile, is scheduled to launch in 2024 and reach Jupiter in the 2030s. This mission is specifically focused on Europa. Beneath Europa's ice-covered surface, a liquid ocean is believed to exist. If this ocean proves to be salty, energetic, and stable enough, it may possess the necessary conditions for life. That's why Clipper is equipped with radar altimeters, spectrometers, and thermal imaging cameras. These instruments will be used to detect structures beneath the ice and analyze any plumes of water vapor that may erupt from the surface. These new missions could reveal more than just the structure of the Jupiter system. They may also help define where the possibilities of life begin and where they end. So what do you think about Jupiter? Let us know in the comments, and we'll see you in the next video.